Hi, I'm Marie. I'm a PhD student here at NBI. Today I will talk about searching for supernovae, which are a necessary condition for neutrino fast flavor conversions. So Shashank already gave a very nice talk about this, but just to briefly summarize the motivation, neutrinos are produced in excessive amounts in Cornelius supernovae, and they play a very important role in the supernova dynamics of the explosion by the heating and cooling of the material, and also they play a role in the subsequent nucleosynthesis of heavy elements that takes place. In these very dense environments inside the core, neutrinos can actually interact with each other through coherent forward scattering, and that leads to this change of flavor effectively. So, for example, we have an electron neutrino and electron antineutrino that scatter of each other and produce a corresponding neutrino-antineutrino pair of a different flavor. If we actually take this phenomenon into account, that in turn also affects the supernova dynamics and the nucleosynthesis. But in order for the neutrino fast flavor conversions to occur, they need some special conditions. What happens is that neutrinos are in the core isotropically distributed because they are trapped and just interact with each other and with matter. And then as the neutrino density decreases, they start to decouple from the medium and become more traveling in the forward direction and eventually free stream. But this decoupling is dependent on the neutrino flavor because they each have a different cross-section with other particles and also the energy as well. So what happens because of this different decoupling radius is that neutrinos become forward peaked in a slightly different way. So here we see for electron antineutrinos, they are more forward peaked than electron neutrinos. Yeah, this is like the forward direction and this is the backwards direction with respect to radius. So because electron antineutrinos decouple at a smaller radius, we will see that we get this crossing in the electron-neutrino-lepton number. And this is interesting because we know that this can trigger the fast neutrino flavor conversions. And that means that if we want to study this phenomenon, we actually need to know the angular information of neutrinos. But the problem is that most supernova simulations don't have that information because it's very computationally expensive. So instead, they evolve only the angular moments, which integrate over energy angle. So that is usually a two-moment scheme. So you have the 0th moment, the number density, and the first moment, that is the flux. So the question is, how can we obtain the angular distributions from this? So one way to do it is to solve the Boltzmann equation that Shashank also briefly went over. So this is like a very simplified version in one dimension, where we just have an advection term describing the transport of neutrinos. We have the density matrix, which describes the number densities of each flavor. And then we have the collision term that describes how neutrinos interact with other particles. And this information we get from the supernova simulation. And so what we do is we solve this equation in a spherical shell from a certain minimal radius to a maximum radius that encloses this region that we're interested in where the neutrinos are decoupling. And then we solve the Boltzmann equation in time until a steady state is reached. So as it's important to underline that this is not a fully like a full supernova simulation. It doesn't have any fluid properties. It's just the neutrino transport in this very local region. But what we do in order to make it more realistic is that we take from supernova models this information about the density, the temperature, the different particle distributions and so on at different post bounce times, so different times during the explosion, to understand how the neutrino flavor conversions occur at different times. And what we did in the study is we compare 3 different metals in 1D because we're interested in knowing if the ingredients in the supernova simulation actually affect whether the ELN crossings are formed. So in this case, we have some simulations with the inclusion of muons in the simulation and some with the inclusion of convection, which is convection in the protoneutron star region that is an approximation made to fit into 1D. So what we see when we solve the Boltzmann equation looks like this. So instead of the angular distributions, we here plot the ELN distribution, which is the difference between the electron-neutrino and electron-antineutrino distributions. And once we get a crossing here with 0 is where we have the ELN crossing. So here I show for 2 different metals with and without convection. And we see at 2 different radii as well that we have crossings in all cases. And that the distributions are forward peaked in the forward direction. But because, as I said, in the supernova simulations, we don't have the angular information. And what if we don't want actually to solve the Boltzmann equation, which can be quite cumbersome? There have been proposed some alternative methods to use the angular moments from the simulations to reconstruct how the angular distributions of neutrinos might look like. And one of the more used ones is called the maximum entropy distribution. And it takes as input the 2 moments as shown here. So when I plot that on the same figure, we see that we do reproduce the crossings. So in all cases, we have these crossings, but the distributions are not as forward peaked as for the Boltzmann solution. Another alternative method is to describe the distribution as like a quadratic function, where we have these 3 parameters, A, 0, 1, and 2, that are described by the moments. So in this case, because we have 3 parameters, we use also the second moment, which is calculated from this Minerva closure. But I won't go into details about that. But once we do that, it looks something like this. So the Minerva closure, it does not work that well compared to the other 2. First of all, it finds double crossings, so both in the backwards and the forwards direction, which could in principle occur, but the thing is that at these radii that I'm plotting, we don't expect a lot of flux in the negative direction. So even if there was a crossing there, we wouldn't expect flavor conversions to have any impact, basically, because there are no neutrinos. So it's kind of a false advertisement that there are crossings now in this kind of distribution. And also you see that the peak is in the backwards direction instead of the forwards. But I just showed some representative radii, but if we now look at the whole radial range, now here at a very early time after core bounce, we see that so this is like the average electron-neutrino decoupling radius. And for all 3 models with the Boltzmann solution, we have crossings occurring just after the electron-neutrinos have decoupled. And then they also cover even up to the pre-shock region. The maximum entropy solution works quite well, except here at the large radii, there are some cases where it only reports crossings every other radial bin, which is kind of peculiar. And then the Minerva method doesn't show any crossings at all. At a slightly later time, we see that actually convection plays a role into whether the crossings exist or not. So it's only in the first model with out convection where we have crossings in this whole range, which the maximum entropy does reproduce, but then it also identifies crossings for the other two models that are not there with the Boltzmann solution. And again, Minervo has no crossings, but there is one example where it does find crossings in Minervo, but only for one of the models. So it just doesn't seem to be very trustworthy at all. But again, the maximum entropy performs relatively well with respect to the Boltzmann one. Right. So that brings me to the conclusion. Fast neutrino flavor conversions play an important role in the supernova evolution. They can develop when we have ELN crossings, but in order to probe where these exist, we need angular information from the Boltzmann solution, or we need to have an alternative method to reconstruct the angular distribution. The Boltzmann solution shows us that including convection in the simulation does play a role, whether you have crossings or not, and at certain post-bounce times, and that muons don't really have any play any difference. And then that the maximum entropy method, if you were to use an alternative method, that performs a lot better than the Minerva method, but it still fails in some cases or misidentifies crossings. And lastly, the method accuracy, doesn't really seem to depend on the physical ingredients of the model, but it does work better than some post-bounce time than others. But overall, you have to be really careful if you only use these approximate methods instead of the full solution if you want to understand where flavor conversions occur. Yep.
Thank you, Marie. Are there any questions?
Yeah, thanks for the nice talk. This is maybe a bit naive, but how exactly do you model the convection? How do you include convection effects?
So it's not in the supernova simulation. It's not something I did. It's our collaborators in Munich. So this is in one dimension, right? So usually you don't have convection, but they have this mixing length treatment where they kind of simulate they know from 3D simulations how it would look like, and then they kind of impose that in 1D.
Oh, I see.
Yeah.
Okay. Yeah. Thanks.
Thank you for the very nice talk. So I have basically two questions. First of all, what is the motivation of choosing this profile in the Minervo method, like the angular profile? And second, do you have a sense of why the accuracy of the method depends on the post-bounce time? What is this critical underlying feature that might drive the accuracy of the method?
So the reason why in this study we chose the Minervo as one of the method is because it's something that's used in the literature already. So that's like the motivation, because people have tried many different methods using the moments to find the crossings, and that was one of them that has been used. So we wanted to show why it doesn't make sense at all, basically. And it comes from, it's a closure used in the supernova simulation to close the angular moments, right? And the other question was why the post-bounce time has a role. I think it's because, so I don't show here, I only showed the distributions at one time step, but it's at some earlier times, it's not as pronounced, the forward peakness of the distributions as in other times. So I think whether the method, the alternative method captures the crossing is also depending on how steep the profile is actually for the true solution, whether it works or not. Yeah.
Okay, so let's thank Marie again.